Good. All right, I guess I didn't. All right, so we got, let's see, so there was like one question about the homework. Anyone have any questions on the homework? Anyway, there was one, yeah.
I don't really understand what you're asking for in the last part. I don't know how you
Yeah,
cartoon for E.
oh,
Yeah.
yeah, so someone asked like D and E couldn't figure out what was going on, and then somehow, I guess I made it italic here, like, there is like a question, even though it's like a lot of words. And then, so D, it's basically, I mean, you can read what he does, but basically he does this spin coating. So you can Wikipedia spin coating. If you want, basically make a solution of the polymer. Silicon wafer. It's like a polished silicon wafer, and then put on a vacuum thing, and kind of a spinner, so it's got an enclosure so it doesn't fly off and hit you. And you put a drop on it and it spreads out. So if you want to make thin films, that's how you do it. It just the solvent evaporates right away. And then I don't know, it's pretty common to make thin films that way, or in the lab, so anyway, so that's what he does. He makes a thin film that way. He ends up with 40 nanometer thickness. So you can usually measure the thickness with an ellipsometer. So there's a machine that measures the thickness. And then he takes those and anneals them. And he says within that 40 nanometer thick film, it's going to act like a bulk sample. He needs a thin film so he can shoot the microscope through the film, because he won't be able to image it with the fluorescence if it's thick. So he has to have thin films to do the measurement. Anyway, so anyway, he claims that he spends some time talking about how that doesn't distort the sample, the polymers in there. So I think that this one's just like comment on that. Then, so that's D. Hopefully that's okay. I mean, it's kind of like just fish around the paper and critique it. They're not used to critiquing papers. So the idea is like to take that approach to everything you read. Books are usually okay. Sometimes books are funny, but papers you should never trust. Anyway, so basically you want to be looking critically at everything. Not that some parts you can believe. I mean, and you can use papers to justify your own biases. Like so you always approach something from your background, so you're going to have biases. Then you're going to say, well, then it's going to go this way. So like you throw the bowling ball, it's going to go down the alley. It's not going to go flying all over the place. So you're going to do an experiment. So you find some papers where people bowled, and the ball always went straight down the alley. So you say the ball will go down the alley. But you throw it, and for some reason it flies off. So you try to, anyway, anything you do, you're going to be trying to justify some kind of bias that you have about it. Anyway, so he's doing that too, and I just think he's right, in what he says, but so you can make your own opinion. And then this equally, yes, I can hear you. That's good. Comment on the ability. All right, so first thing, that's a question, right? So he goes through the process to make that film, and the bottom part is stuck to the glass. It's adhering to it. And then he takes that and he puts toluene onto it and swells it 20%. So he says that's like a bulk expansion. Like the same thing as if you took the rubber or something and put it into a solvent and it swelled. Right, but it isn't the same because the bottom part is stuck in the top part. So it can't, or for one thing, it can't laterally expand because it's fixed to the surface. So it can only expand up and down. So it's going to be a uniaxial expansion, not a triaxial. Yes, like there's uniaxial, biaxial. I guess it's triaxial or volumetric or dilatometric they call it. Actually, no one uses the word triaxial. So it's like dilatometric. Biaxial would be like if you stretch out a film in two directions, or if you take like chewing gum and squish it, that's a biaxial. And then uniaxial is like you pull the beer can lid thing. The thing holds the beer cans together and stretch it. Tensile is a union. So anyway, so basically it matters like what kind of deformation happens when he swells it, like in terms of how the structure changes. And he's saying that he's saying that none of that happens. That's uniform swelling, that the side chains expand and that makes the persistence drop when it's swollen. So when the side chains, so say they're uninflated balloons stuck to a rope, when you inflate all the balloons on it, and all of a sudden they make the rope straighten out as the balloons push each other. So that's the idea. So anyway, that's his idea why it drops here. I think that there's some other explanations for why it drops here involved in the experiment. You know, so that's all. That's just comment on that. If the tag chains are more likely to be normal. There's also an issue that he's looking at a projection. So there's another issue, like if he's looking at a projection, so say he's looking at a projection of these things. So if they're confined to the surface, then the projections, he's going to get more persistence. If you loosen them up and they can tilt some in the projection, they would have a shorter persistence, like in projection. Right, like if you look straight onto the rods, they have no persistence at all. That way they have a finger persistence. That way they have half a persistence of the finger in projection. And so there's some issue about, right? So if you draw a cartoon, so it's basically like try to get the dimensions right. It's the issue here. So in your cartoon, so you can see if this thing could work. See. Oh, that's nice. You have, so say he's got this, so this is infinity in the directions that way, and then this is 4. Okay, 1, 2, 3. 1, 2, 3, 4. Right, so that's 4. And then his the length of this thing is the length of the thing is like half a micron, so like 500 nanometers. 10 of those 40s, like 1, 2, 3, 4, 5, 6. That's 6. So that's the length of this thing. And the chains he has have 2,000 molecular weight balloons on the side, and those probably have like that whole thing is probably like maybe 10 nanometers diameter. So maybe the diameter of this thing. So you can say, and then the length of this is 250. So so actually the 6 of these would be the length of the persistence unit. Right, 40, let's see, that's 40. 4 times 6 is like something like 250. It's 4 times 5. So say it's so he's got 10 nanometers is one of these. So he's got things like that, and then the persistence of it, he's claiming is like that. Like, see what I mean about drawing the cartoon? Things start to look pretty funky. Like something's really wrong with this whole thing. Let's say that's right. This is the dimensions of what he's describing. He doesn't draw a picture out for a reason. Like, and then he's got some kind of a kink of 60 degrees for the persistence. Right? Well, that's not possible even. Right? You can't, like, well, I guess it can come towards me, right? So it can come out of plane towards you. Anyway, if you start drawing the thing, you start to realize, like, and he's going to increase this by 20%. So 8, so one more notch. It's going to, this is as tall you mean swelling, it's going to go up like that. And maybe the projection thing doesn't even matter because the whole thing is pretty bogus, like to begin with. So once you start putting the dimensions into this thing and try to make it look right, it doesn't work out. Like what he's saying, this thing's the same thing. If I could like scale down, right? He's saying that this thing is like kind of like random walks, like his models like that, like persistent chain walk things. Right. In other words, I scaled it down so that window is like a little window like this, expanding up. So I'm saying like this is a scale bar of 40 nanometers, and this is a scale bar of like 10 micron. So I've scaled, this is a scale up of that. And you look really confused. Right, so what's the problem?
So the big one's 40 nanometers and the actual one's 10. Is that what you're saying? The one in the middle is 10 nanometers?
The diameter of the thing he's making is about 10 nanometers. There's 2,000, 2,000. So it's basically 10,000 grams per mole chains. Like if they're Gaussian, something like 10 nanometer.
So they're so swollen up that they're not actual.
Oh, when they swell up, they're going to get larger. This is unswollen.
Oh, okay.
Yeah, when they're swollen, if they're straight, right, then this is more like going on the order of 40 nanometers. If they're fully, in other words, these are like little curly things, right? And say you go to your hair straightening salon, and that curly hair becomes like straight hair. I mean, so it gets much longer, you know. So yeah, I'm saying like, so this is what you should do when you read this paper. Right? He never shows any cartoon, so he's kind of left it up to you to draw a cartoon of like what's going on. When you start drawing the cartoon with the numbers that he gave you for the sizes, then you find out that the thing is like pretty nutty. I think it looks pretty nutty at some point. And all the other thing, I mean, there's a lot of things like here he's showing, all right, so that he's showing these, there's a lot you could say, you know, I mean, he's showing these pictures and saying that that's a chain, you know, but it isn't a chain at all. And it so the size scale here, does he say what the bar is? Anyway, I think the coils of the chain are within that bar. So the chain itself is actually tortuously wandering within that white spot, right? Which is already computer enhanced, so that actually you don't have any idea what you're looking at, especially given that he starts with this, throws away all the blue, ends up with the white, and computer enhances it. So by the time you get to here, like what's going on, and even if you take the numbers, if you believe the numbers he gives and draw the cartoon, like it doesn't pan out, like it looks goofy. Is that any better, or I don't know.
I think so. But what does he mean by real chains? When he was talking about that, I kind of confused about that. You think he chose 10% to be actually in the last sentence?
Okay, could this account for the observed 10% decrease? So this is a 10% decrease because this doesn't start at 0 here. So actually it's within the error bars. That's another issue. It's like when the error bars overlap, that means you don't know anything about it. The only thing you can say is when the error bars don't overlap. This number, that number, and that number are the same number if they're within the error bars of each other, which they are. So that means there's nothing to distinguish there. But if you said that the lines are true, then it's 10% shift, which isn't much of a shift. It looks like more because he's reduced the scale range here. It doesn't start at 0. And if you start at 0, it wouldn't look like much, especially with the error bars. So this paper has a lot of problems, like pretty serious. They should have come out and reviewed, but didn't, for whatever reason, you know. So I don't know. Does that help any, or can you? I'd like to see you smile or something instead of like.
I don't know.
It's a matter of like looking at something and just saying like, okay, so he's telling you something. He's trying to sell you something, and are you going to buy it or not? You know.
Yeah, I was just confused by the diagram that you drew, but it's.
All right. I mean, all I did was take the numbers he lists in the paper and try to draw a picture of like what that might look like. Right. And then from that, once you can draw a picture, then you can say, you can start predicting behavior, you know. So you do some measurements, you get some numbers, they have error bars. I mean, that's your confidence interval in what you're saying. And then you got to put it together, like coalesce all that stuff into something that means something. So a picture is a pretty good way to do it. And then from that, you can predict some things like there's definitely 100% of confinement effect inside that film. And there's no question. If you try to draw it out, it looks insane. It's totally confined, like it's totally just pegged there. You know, it's as if you took the hairball and like totally squished it. You know, and then it's not going to have the same persistence as it was when it was a piece of dust flying around the room. So anyway, just try to, you know, I mean, there's no right and wrong to this. It's just like a way to train you to get to look at things critically instead of like just say, oh, it's a paper, it's published in PNAS. This is the best journal. This has to be true. Right? It absolutely has to be true because it's in PNAS and it couldn't have been published there any other way. But PNAS, right, if you remember the National Academy of Sciences, PNAS automatically publishes your papers. And then also, so this one, and most of them at the end, it's going to have a recommendation. This is the paper, but so you can also get into it by someone that is on National Academy of Sciences recommends this paper. And then it gets published. And then there's like a third route, which is like the grunt route, which is like you submit it to them and then they reject it. And then you beg them and then finally argue and you get it published. So there's like 3 ways to get into this high prestige journal, so anyway, so in this one, this was a suggested article. It was suggested by someone in the academy who's like probably at Northwestern, so it's kind of like, or it was his advisor or something like that. So I mean, anyway, it's nothing really that it has to do with persistence, but other than that, there's not really that much to gain from this paper. But well, Blanco polymers and then brush polymers are a popular topic. He's using metathesis polymerization. So there's a few things that are kind of interesting that would be useful to you at some point. Could be useful. Like you're doing polyolefins, metathesis is one of the main routes now to make polyethylene. Right, so make these controlled low crystallinity polyethylenes, linear low density stuff. They actually, I think they call it metallocene polymerization, metallocene polyethylene. So any other questions on this thing?
I guess just a kind of a reflection question, I guess. What would be like, are there any other, you think there'd be any better techniques to study for like the persistence for it and whatnot?
Yeah, you should have just done, yeah, absolutely. The reason this got published is because in this journal is because it's a new technique.
Yeah.
Fluorescence microscopy. So you're working with 0.6 micron light. You're measuring like atomic dimensions because you tag it with fluorescence and somehow use computer enhancement. Right. So, I mean, that's kind of why it's in here. So, but the normal way to do it, you just stick this stuff into get deuterated toluene, or somehow you just put the chains, or you deuterate some of the chains, and you can use neutron scattering to directly measure the persistence of the things. That would be the simplest thing to do. And the second thing would be to just do a simulation of it. Just use lamps. Plug in your molecule, say what's the persistence, let it run for a while. That would be a pretty simple thing to do. And
kind of new to all the techniques.
Yeah, so you can also kind of get it from rheology. I mean, so you can do the rheometer measurement and get the crossover at the high frequency and say, like, I can get the persistence from that. That's a little bit wishy-washy. So there's a couple of ways. I mean, you get the Kuhn length, and it's half of that is the persistence length. So that's kind of those are the options. This is nice because if you get a picture of it, I mean, but I don't think he can do it really the way he did this. People do like, I mean, people do all kinds of things to get persistence. Like you can do an AFM with AFM. So AFM has a tip, and you measure the association with the material underneath, and then you can map out on atomic scale what things are. You can also attach to the AFM tip a molecule and then drag it out, and from the stress strain on the molecule, you can get the persistence length. Yeah.
So I guess, I'm sorry, I'm back on the cartoon for you.
Okay.
I guess the confusion that I had is when you put in the 40 for like the length. So I thought the entire chain was 40. But you're saying.
Oh, no, the diameter, say the diameter of the chain, right? But
the diameter was.
No, his persistence length is 250 in the plot. Like this one, there's a plot of persistence length there, right? So this is all like 250 nanometer. So that's the persistence length. That's just the step length of the chain. So however many steps, so it's going to be longer than that. Yeah.
So what you're saying, you can only really do it if the persistence length is smaller, or not, yeah, the persistence length is smaller than the thickness of the film?
Yeah. Yeah, if you put just a normal polymer in there that has a persistence length of like 1 or 2 nanometers, then maybe you could do it with that. But he doesn't have the resolution to go down that small.
Yeah.
So his technique is tied to the 250. So it's a catch-22. He needs 40 nanometer to see it, and he can only measure 250 and above. So it means he can't do it. Right? I mean, I think he can't do it.
So if you have a smaller way to visualize it, you should be able to do it, you just can't.
Right. Yeah, I think he can't do it. I think 250 is kind of his limit. Yeah, see, right, his error bars are smaller at the big end and then they get larger at the small end. So 220 is already into this range where things aren't that resolvable. Maybe you can go down to 100 nanometer. And still, he's got to have a 40 nanometer film to see it, to use the technique. So it's limiting. It's maybe a good idea, yeah.
So the film thickness is 10 nanometers.
No, the film thickness is 40 nanometers. That's why, yeah, so the film thickness is 40. So the first thing you have, he says that,
Is there a difference between when we're saying film and like this chain, like that chain is a part of the film?
right,
Correct.
the films, yeah, right, the film is made up of chains. So he's got some chains that are tagged with fluorescent groups, and then it's in a mesh of other chains. So it's all chains. The
Okay.
film is entirely chains. Except when he puts toluene, and then 20% of it is toluene.
Mhm.
And supposedly it evenly swells with toluene. I mean, the other thing is that this side of the film is fixed, and this side is free. Right, so when you swell it by 20%, I mean, maybe it's gonna look like something like that going on. I mean, it's hard to tell what's going on once you swell that by 20%. I mean, I'm saying that it would just swell up, that's it. It could also swell like that, and then who knows what happens with the chains that were originally like that. Maybe they go do something else, like when it.
So the individual chains are 10 nanometers that compound to make a film of a thickness of 40 nanometers?
Yes,
Or
but then, and then the step length, notes there are a rod for 250 nanometers in the planar direction of the film.
Okay.
So, I mean, he doesn't say that, but basically that's the only way they could be 250 nanometer rods, right?
Mhm.
And then the total chain is made up of these things into something like that.
Right.
So basically, you'd have to scale out to see, you have to have another level of your cartoon to see exactly what the big picture is.
Right, okay.
And how that would be confined to something that would be basically the thickness of that line.
Mhm.
You know what I'm saying? Like,
Yeah.
once you scale out to microns, your film is aligned, you can't even see the film.
Mhm.
So all this squiggly stuff has to somehow be squishing the hairball into this flat thing, like a sheet of paper. Somehow. So how you do, so,
So
you know what I'm saying? So the only way to figure out like what's going on with this thing is to draw that picture, I think.
Okay.
Because otherwise you go, oh yeah, 40 nanometer, 250 nanometer, no problem, woohoo. A half a micron, oh yeah, okay. Right, and all these numbers flying past you, like you're on a highway and there's a sign saying, eat it, Joe's or something. So like, really have to stop and put all that stuff together into your own picture and say, how does this fit in there? Like, there's not enough room for it to. So. Anyway, hopefully that's enough. Get back here. So, yeah, all right, so I guess I'm on, let's see, all right, 10:35, so I should have enough time to do that thing I did last time. And kind of, it was kind of too much, right, so. Not 73, that's done, kind of. Oh, what slide is this? Slide 26, I didn't write it down. All right, so this is this business about this Einstein paper, 1905 thing. So I wanted to go through that. So this, all right, so let me try to do it again. See if I can do it over here. Okay, that's why I put this here, so I get to have both things open. This is one disadvantage of the system. Slide 26. All right, so there's two parts to this paper. Right, so let me get rid of this. I apologize for the handwriting, it's kind of like too late to change it. So anyway, so there's two parts of this paper. Like the first part, so we say like if we have the chains, and then they can have all different lengths, right? So we have that distribution. So we say that distribution is going to be Gaussian, or it's bell-shaped distribution. So the probability of any size R peaks out at 0 and then can go in either direction. So you can think like we did a bunch of simulations, if we add them all together, we end up with kind of a cloud of probability with a peak in the middle, right? So that kind of probability, it can't depend on X because this is minus X and that's plus X, and it's the same on both sides. So the best you can do is X squared. That's like the lowest level of describing it that you can get, right? So you have like, it's got to be X squared, it's got to decay. So you end up with this Gaussian function, minus X squared, and then the Gaussian is 2 sigma squared per 1D Gaussian. For 3D Gaussian, you cube it. So you end up with exponential minus X squared over 3X squared over 2 sigma squared. This is 1D, that's 3D. I guess 2D would be 2X squared. But anyway, so this is, for a 3D Gaussian chain, this is the function that describes the ambient distance dependent sort of thing, right? And this is the same thing as a Brownian walk, right? So the first part of this paper is saying like, why is the average length? So Brownian walks instead of average of R squared. So the average of R is 0. The average of R squared is the first meaningful way to measure it, which equals sigma squared for the Gaussian. And then we showed that this number equals NL squared for a random walk, because that thing's going to be this double sum of this Ri dot Rj, and the only ones that matter are Ri dot Ri, so it's R squared and this N of those, so it's NL squared. So we got that before. So Einstein wants to, so the analog to that is a Brownian walk, which looks exactly the same, ends up with all the same scale and stuff. And in 1905, there was, what's the guy's name? Staudinger was a guy at ETH in Zurich, and he said that polymers were chain molecules in like 1920 something. So this was like 20 years before they knew polymers existed. Before that, they thought it was just kind of like the one like micelle, just a collection of associated gunk that's stuck together somehow. Like when they found rubber, things, natural rubber and stuff like that. Anyway, so this Brownian motion predates about 20 years the business about polymer chains, and then once Brownian motion was all developed, then they could just be lifted and put into polymer chains. So that's why I looked at Einstein's 1905 thing, because all the information about polymers kind of is based on that in a sense. Like the idea that it's Gaussian, it could be that function that describes ambient distance is based on Brownian walks, right? So anyway, so that's that. So to do this, he says, so he's looking at a particle moving in time, and he's saying it's like a collection of particles, so he gets the average. So instead of talking about a single particle, he talks about the density of the particle as a function of position and time, right? And he says he can talk about that in terms of the time dependence, right? Or he can talk about that in terms of the space dependence. So it's got space and time as the arguments to the density. The density is changing with time, it's changing with space. Right. So he's saying that those two have to be equal to each other. Right, so there's a difference between space and time. So time goes in a one-way street, right? It only goes in the positive direction. That means that the first derivative exists for time. So if you want to know the simplest state for time, you take the thing now and then how it changes with time. So the first derivative, forget about the higher derivatives, which don't matter as much, right? So you say, I have the position, the distribution is now, so time is like time zero, plus the change in time is, which he calls relaxation time for reasons later, and then the derivative of this xt with respect to t, and there's going to be other terms, but he's only dealing with the first order terms here, like the most important things. That's his time dependence. It's one directional. It has the first derivative as the argument of the thing. Then he looks at the space and he says, well, the space is going to be governed by some distribution, and that distribution is what he wants to get. So he has the density at x and time, and he's going to integrate over that unknown distribution over the spatial part. From minus infinity to infinity. And then he's going to start adding the derivatives to that. So he has this first derivative, d rho dx, xt, minus infinity to infinity, and then it's the first derivative times, and it's going to be x times this distribution function in space. Okay, so if it's a symmetric distribution function because of part, yeah,
What does the subset G?
Gaussian, but he doesn't know it's Gaussian at the start.
Okay.
So it'll be Gaussian. He doesn't know it's Gaussian. It's a Gaussian distribution in space, but he doesn't know that. So it's just easier to say it's Gaussian because later on it'll be Gaussian. But anyway, but you know that one thing you know is that you started here. It's random diffusion, so it has to be symmetric. So the pluses have to kill off the minuses in space because it's symmetric. Time isn't symmetric. Only there's one way. Space is symmetric, so there's no first derivative. The average of this x goes on this side, x is plus, on that side, x is minus. That means the integral of that is zero. That term has to go away. So you don't have a first derivative in space. You don't have, you have it in time. And then you have this second derivative, dx squared of x and t, and then integral minus infinity, delta x squared by 2, because it's a Taylor series, so you do squared by 2, cubed by 3 factorial. It goes like that. And then this same distribution function, d delta x. Right? So he's going to just take that will solve, that's a solvable integral and has a value. That's the argument. So this is just going to be a number. And then he has this second derivative and this first derivative. And on this side he has rho, and the integral of this function is 1. Because it's a normalized distribution function, which means that the integral of it is 1. That's the definition of it. So this thing integral, like the integral of this Gaussian is 1. That thing's 1. That means you have rho x here, and then you just have this differential equation like d rho d time of x and t equals the second derivative dx squared. And then times this prefactor, which will be this thing divided by tau, which you divided by 2 tau. So that thing you just define as the diffusion coefficient. He just defines it that way. That's the definition of the diffusion coefficient. The change in x, integral of x squared by tau is the diffusion coefficient by him. So then, so this kind of differential, so if you have the derivatives in the solution to that differential is just an exponential. So it's a Gaussian. Basically, that's how he got the Gaussian. He set up this thing where he has time dependence, space dependence. Time dependence is only goes in one direction. This goes in 2 directions, throwing off the first derivative. You have the first derivative as a second derivative. And that ends up giving you this exponential function for the so the density is a function of x and t. It's going to be how many particles are in the system. square root of 4 pi gt and then a Gaussian. Over 4 dt. That's a solution to that differential equation that we got. So that also tells you that, so if this is a Gaussian, so this should be x squared over 2 sigma squared, so that's sigma squared is 2 dt. Sigma squared equals x squared equals 2 dt. And so that's the definition of Brownian motion, that you get square root of time for the distance traveled. In other words, so this thing is the definition of diffusion. That's like how you define what diffusion is. You look at the distance traveled, so the root mean squared, the distance traveled is going to be the square root of time. And the prefactor of that is going to be the diffusion coefficient. Right, so in that case, like, so this is what Brown had observed in the 1880s, I guess, 50s, 80s, and then like 40 years later, he proves how it works, like how you get that behavior. That was a good thing, right? So you got that. So that's part one of this thing. Anyway, it's good to go through these things. It might be a little dry, but any questions on that thing? I mean, it's pretty dry, but basically it's good to go through this. No one else is going to go through it. You know, so I'm left to the task. Then the second part of this, so that's really the end of where we are in polymers, like the Gaussian function, right? And then this NL squared thing, right? So but later on, when we look at transport of polymers, then we need to know the Stokes-Einstein equation, which is this, like the diffusion coefficient is going to be, so the higher the temperature, the higher the diffusion. Right? In other words, D here, so the bigger distance you travel if you have a higher temperature, biggest average. So in other words, you're doing this at a low temperature and you're doing this at a high temperature. That's kind of the idea of this diffusion thing. So temperature governs the rate or the distance, kind of average distance as something moves. And then that's modified by this Stokes law, the viscosity in this hydrodynamic radius, which is an equivalent sphere. So in other words, in terms of transport, a sphere of that size would have the same transport as that thing. Right? So there's some kind of equivalent sphere that has the size of RH, radius of RH, that moves the same as that big thing. That's what Stokes' law is talking about. So you have an equivalent sphere. So this is called the Stokes-Einstein equation. And this is the result of the fluctuation dissipation theorem, which is kind of what this paper is about. Right? So it's basically how did thermal fluctuations, which is diffusion, mitigated by bulk. The viscosity is a bulk parameter. Right? And hydrodynamic radius is kind of a nano parameter. So you have bulk, nano, and then thermal kind of mixed together. So dissipation of fluctuations. That's what this theorem is about, and this is kind of like the main equation for it, is the Stokes-Einstein equation. So you see that equation like over and over and over again. So how do you get that thing?
Professor, real quick,
Yeah.
sorry. Can you remind me what the symbol is to the right of pi again? Sorry, I know you said it last time. But
Viscosity, I think it's
Viscosity,
eta or something.
Eta.
Say, what is it? Zeta.
Eta.
Eta? Okay, it's some kind of Greek letter.
Yes.
Yeah, it's eta, I guess. So that's just viscosity. Sometimes, all right, you can also see mu
Yeah.
for viscosity. There's probably
So, yeah,
some other
that's what you
symbols.
Is the K Boltzmann constant?
Yeah, that's KB, yeah, Boltzmann constant. It's always, so this is kind of temperature converted to energy. KT is energy. That's in thermal energy. Right, KT is always thermal energy. So everything's going to be balanced against KT. So you're kind of balancing viscous energy and thermal energy when you're getting the diffusion coefficient from it. Thermal energy is making things move, viscous is making them slow down. The balance gives you this diffusion coefficient, how fast it moves. Okay, so, anyway, so that's, so like, all right, so to get that thing, to get that thing using this business, he has to have a field. He figured out you have to have a field. To make this work. And in the end, the field disappears. It doesn't matter what field you use. So the simple field, he says, is like a 1D gravity versus diffusion. So it has like a battle between gravity and diffusion. Gravity is making everything go down. Diffusions in 1D is making it go kind of shake up and down randomly. Right. So supposedly, and this is governed by KT. And this thing's just governed by G. So the force of gravity is G times the mass, and the energy of gravity is mgh. Right. Or mg, I guess. Normally. That's kind of the force of gravity. And the force of the drag is going to be like the velocity of the gravitational terminal, kind of the terminal velocity for this thing falling and subject to diffusion up and down. So it doesn't, so anyway, that velocity times the friction factor. So in the friction factor, this is Stokes' law, 6 pi times viscosity times height and radius, so equivalent sphere radius. So you have something falling. It could be a pollen grain or whatever. It's subject to this force, and then you have this mg force on the other side. So you can say that, you know, I can solve for this gravity velocity is going to be mg divided by 6 pi times h. So I have that equation. Right. Kind of the first equation, the grouping of some equations here. So then he goes into this, back into this kind of, all right, so then he says that all right, so say you have a lot of particles falling down, right? And then there's going to be, if you looked at the density as a function of h, right, so it would start at some value like rho 0. And then he's expecting that this thing would, the density of that would go like that. And that function is going to be Boltzmann's law. So you have the energy of the particle going by gravity, and then KT driving the diffusion. So in other words, this is like an energy balance between the thermal energy and the gravitational energy. And the solution to it is this exponential decay by Boltzmann's law. So that's kind of like the density is a function of h. Some of these things are not that obvious, like why. I mean, you know, this is what he said, you know. So that's his proposition, I guess, for this. So that's going to describe the way this thing. That's kind of like 2, right? In 3, he says he has flux. So the flux is defined as J is going to be the density times the velocity. And it's a 1D density and a 1D velocity. Everything's 1D here. So it's a 1D flux. Right? So then he also has Fick's first law, which is that the flux is the diffusion coefficient times the change in density. And he has this nice function here for this. So I can write a derivative of that. So you can go to the derivative of the density with height, going to be the rho 0, and then you take the derivative of this thing with height, which gives you negative mg over kt, and the derivative exponential is exponential, mgh over kt, right? And then realize that rho 0 times that is density. And you say that this is minus mg density over kt. That be rho dh. And then you can say you have rho times velocity has to equal this negative d. So d rho dh is this mess, which is mg rho over kt, and the rho's cancel, and you have another velocity here. That's a velocity due to whatever. the distribution function and the flux equation fixed first law. So he has two velocities, that velocity. He also has the velocity of d. He also has the velocity, the other velocity, v of mg over 6 pi viscosity h, right? And those two are the same velocity. So then you say mg cancels, you have d, so you have d equals kt comes up, and you have the Stokes-Einstein equation. So you just have that thing after that. You can see the guy was a little convoluted in his thinking. He was able to pull some things out of his hat. So, all right, so how did he come up with this thing? I propose that he knew that the diffusion coefficient had to be proportional to temperature. And he knew that it had to be inversely proportional to the drag coefficient. So he just wrote that, okay? I mean, he just wrote that because it was obvious that's what it had to be. Or he could recognize that it was obvious. Maybe he had to know something. And then he went back and he figured out, how could I possibly get this things? And he realized, like, oh, I need two things to be equal. And I needed this thing. He knew this Boltzmann thing that's floating around in 1905, like the Boltzmann distribution with temperature. Basically, it's a backwards derivation, because no way could you possibly think of this forward the way I just did it. Right? In other words, he knew the answer, then went back and got it. I mean, Debye was asked about this once, about how he derived things. And he said, like, my advisor when I was in grad school asked Debye this in a cab. And Debye said, of course I knew the answer before I did it. You know, so you have to kind of look at these things and think, how could he have possibly come up with this? And then, like, you have to go back and say, the thing that he came up with is obvious. And like, all you have to do is piece together how to do it. Right? So no one's gonna, so basically what you get is obvious and no one's gonna argue with your conclusion. So then that's how you become a genius. Right?
Is the flux, does that kind of have to do with like when you like magnetize parts and whatnot as well too? Or is that a different type of flux?
I mean, there's a lot of fluxes. This is just the Fick's law is just the diffusional flux, like how particles. So the particle has to move down in concentration gradient. It's going to go from high concentration to low, right? So it's a negative. So it'll be a negative concentration gradient that drives flux. And then the parameter that decides how it fluxes is a diffusion coefficient. That's also an obvious thing, I guess. Like if you have a big, huge concentration gradient, it's going to be a lot of flux. If you have a little teeny one, there's not going to be much flux. And then just invent some number that relates it to, and that's got to be the diffusion coefficient. You know, and then the other one is just the definition of flux. You can have a, so this is just flux of mass. It's flux of mass, right? So it's mass flux, but that could be driven by a magnetic field, electric field, electrophoresis, flux things, right? You could have magnetic flux, gravity flux. I guess it's driven by a field. This is a concentration field he's looking at. Yeah. So anyway, the gravity field though drops out in this last step. Both depend on mg, g's out. So it could have been any field. It could have been a magnetic field. Could be anything. So it's basically it could be a 3D gravity, 1D, whatever. You know, so it's pretty nice, I guess, to look at that and to think like, I don't know, Einstein, you never see anything by Einstein in the classroom, I don't think. So it's nice to see something by him. I think it's not nuclear bombs or something like that. So, anyway, so there's that business. What else we got? Any other questions on that? Or, oh, you know, this isn't like something you need to know, but I think no one else would go through it. So I might as well do it. I'll volunteer, I guess, but yeah, that's the measurement to get. So this is the kind of measurement you need to get the Kuhn length, and so you need a high frequency. What's next? Are we going to quit, or we can quit? I don't know. Let me just do this one thing and I'll go through it again next time. It's simple. Like you have here. Let me just do this. All right. Then I can go through it again. So we have, this is the 3D Gaussian, and I'll show you how to get this prefactor. Like this isn't trivial to get that prefactor. So I'll show you how to get that mathematically, but basically this is the normalized, the integral of this is 1, and this factor makes it 1, right? So you have to propose the Gaussian, then integrate it, set it equal to 1 and solve what the constant was. And that's the constant that gives you 1, right? So that's a normalized Gaussian. And this is the Boltzmann thing we just saw, like energy over KT. Right? In other words, higher temperature. In other words, you have a barrier energy for something to happen, and it's relative to KT. So if you had a high temperature, then this number is small, and then you have a high probability of the thing happening. And when this KT gets lower, the probability drops because this number will get huge and it's negative exponential. Right? So it's kind of a thermal dependent process. Right? And this is our random anyway, so they're both exponential. So you just say the argument of that exponential has to equal this exponential. So you get this expression, right? Which gives you, for a chain, for a Polymer chain, gives you the thermal dependence of the chain, the energy of the chain. That's nice. So you have that energy. So where you use that is the derivative of the energy gives you the force. So if you take the derivative of that, you get this expression, and then this thing, the prefactor for that from that derivative gives you the spring constant for a Polymer chain. Like what's the modulus? If you take a single chain in AFM that's floating around, you stick the bottom and then you take the other end and stick it to the chain. You can draw it out and you get this spring constant from the chain. Like what's the modulus of it? Also, that's the function that describes rubber elasticity. Like so if you have a rubber, so this is also kind of the equation for a jump rope. So if you have a jump rope and you're swinging it around and temperature goes up, so you swing it faster, then the ends of the jump rope pull in. So the force increases proportional to temperature, right? And then then the longer the jump rope, the smaller the force. So N is how long the chain is. The longer the chain, the smaller the force. So I'll go through this again next time, but so basically some simple comparison of these functions give you like properties, like the behavior of polymers. You know, just having that Gaussian and this Boltzmann thing. Yeah.
When it says it's thermally equilibrated, does that mean that the temperature is consistent across the polymer?
It means it's sat there a long time,
Okay.
so that it doesn't have residual stress in it. Like in other words, it's not, say you just put in an extruder and all the chains are like straightened out.
Sure.
So that's not thermally equilibrated. If you let it sit and anneal, at some point the chain should get back into this random shape.
Yes.
Then that's thermally equilibrated.
So you don't have a time term.
They don't have to, what?
A time term?
Yeah, it takes a certain time. It's relaxation time to get it to go back to that state. So it could be days. It depends on the molecular weight. If the molecular weight's huge, it could be like months, or it could never.
Like one of like the homework problems, I think they don't, and like they talk about how like hands like reference another like equation, and when I was reading up on it, it said that like the equation was like a Gaussian like statistics. And also having exponential decay.
Yeah.
But then later Chan said like that his model does not think like a Gaussian like linear or like follows exponential decay.
Yeah, just literally.
So.
You mean for this, so that thing's about that equation, 2L instead of L or something? It's like S over L, he has S over 2L. And he's saying because it's not Gaussian?
Yeah, like then like later on in his work, he said that like his like like his like bottleneck or whatever is like, you know,
Oh,
Gaussian speed is like it's like a solid particle.
uh-huh.
And so
Okay, I will.
you know, apply something like to a Gaussian model if it's like not technically Gaussian, or is it it's like it's just a model and it's fine.
Well, the persistence isn't really, the Gaussian is the whole chain, you know, and the persistence is just the steps. So maybe it doesn't matter, I guess.
Okay.
I don't know. I mean, I'd have to kind of look at it, but I think that doesn't affect this thing. I think he's maybe talking about something else. So.